Where you go?
All right, so welcome to the third day of the conference, and we're very happy to have Matthew Choptuik, who will tell us about gravitational critical collapse beyond spherical symmetry.
Well, thanks to the organizers for the kind invitation. It's nice to be back in Toronto. And as somebody from Western Canada, you don't know how hard that is for me to say. So here's an outline. I'm going to start by reviewing critical phenomena in gravitational collapse, but in spherical symmetry. And that'll give us a setup for the later discussion in terms of the concepts and the various parameters that are floating around. And then in terms of beyond spherical symmetry, I'm going to talk about several matter models and vacuum. So that will include the Einstein massless scalar, both in axisymmetry and 3D, the case of vacuum gravitational waves in axisymmetry, and the Einstein-Maxwell system in axisymmetry. And then I'll just have a few brief conclusions. And as a physicist, I kind of feel like a gazelle in a herd of lions here. So I have to come clean with you. No rigor here. Okay, so I'm going to discuss black hole critical phenomena in the context of how they were found. So from the perspective of a computational physicist. And so the whole idea was that we set up some sort of a numerical apparatus which has a control parameter which controls the strength of the initial data of a collapsing matter field. So in this case, think of a scalar field that's what we're going to be discussing. And this parameter you can tune back and forth between two extremes. So if you tune it all the way down, then the evolution doesn't form a black hole. But if you tune it all the way up, a black hole does form. And so just intuitively, somewhere in between those two extremes, there's going to be a threshold of black hole formation, and we call that P is equal to P star, where P star is the critical parameter value. Now, if you think about this for a little bit, you can sort of come up with a notion that there's two things that could happen if we consider the mass fraction that ends up in the black hole. And I'll call those type 1 and type 2 respectively. So I'm plotting the mass fraction here as a function of this parameter. So in a type 1 collapse, we would have a mass gap at threshold. Whereas with a type 2 transition, there would be no mass gap, and we would start essentially continuously from effectively a zero mass black hole, although such a thing, of course, does not exist. And so the question is then, what's the nature of this no black hole to black hole transition? And Chris Didulo sort of got me thinking about this in the late 80s. He was also thinking about this, as you know, he wrote this monumental work on the collapse of the massless scalar field. So a central question then is, can one make black holes with arbitrarily small mass? And here again, appealing to some physics, condensed matter physics in particular, we're viewing the mass as an order parameter. So it measures some sort of order in the system, but we have two possible types of transitions here. A first order transition where there's a discontinuity in the order parameter, or a second order transition where there's no such discontinuity. Fine. So what you find when you do these experiments is that no matter how you parameterize that initial data, you choose your parameterization however you want, what you're going to want to have on your apparatus at the end of the day is an infinite set of verniers in order to see what's going on. And so, in other words, this black hole threshold is generically characterized by exponential sensitivity in the initial conditions. And the natural control parameter then is never the P that you chose, but it's a logarithmically rescaled parameter, log of P star minus P. Okay, and so when you do this and you run this sort of experiment, what you find is for many collapse models, and that's a lot of collapse models now, you find isolated in solution space universal solutions. And this question of universality will sort of play prominently in the talk, with additional symmetry. So in the type 1 case, the solutions are either static or periodic. And in the type 2 case, they're the analog, but with scale symmetry. So they're either continuously self-similar, or interestingly, they're discretely self-similar. So the discrete self-similarity is the analog of a periodic solution in scale. And what you also find is universal scaling laws. Again, the universal means here that it's independent of the initial data family that you chose for solutions which are near the criticality point. So for example, in type 2 collapse, the black hole masses satisfy the black hole mass scales like P minus P star to some power gamma, where this gamma is a universal exponent. And here's some sample data for the scalar field, which shows log of P minus P star and log of the black hole mass, which is formed on the y-axis. And so you get this nice, almost linear curve, and the inset shows what happens in the regular parameterization, where we're just plotting the mass of the black hole and the parameter here. So this is, again, indicative of the second order phase transition. Okay, so let me discuss in a little bit more detail this simple model that I studied way, way back in the mid-90s, early 90s. And it's arguably the simplest model for gravitational collapse using reasonable matter, that is matter which doesn't form a singularity by itself when it's not coupled to gravity. And so it's simply a massless scalar field, which is a function of two coordinates r and t. And the initial data for this field then is the field profile itself, as well as its first time derivative. And the dynamics describe imploding and exploding shells of radiation. So that's what's going on physically. And there's a fundamental nonlinearity which gives rise to competition in the model. And that nonlinearity is present for any matter field which couples to the gravitational field. So for the massless scalar field and for all massless fields, the kinetic energy of the field wants to escape to infinity. But if you make it self-gravitating, so there's potential energy in the model, then the potential energy tries to confine the matter within a certain radius. And you can play off those two effects, one against another, and it's essentially that competition which gives rise to these critical solutions. Okay, there's supposed to be a little animation here, but I can't do that with the PDF, so I'll show you the equivalent in a second. So here we can tune the control parameter P to machine precision. So for those of you who aren't numericists, this means we can tune to a part in 10 to the 16th and still see differences in the solution phenomenology. And as P goes to the critical point, you get this unique critical solution. So the details of the initial data are washed away, and you find that the critical solution is discretely self-similar. And again, I'll show you what that looks like in a couple of slides. So the curvature grows without bound in the precisely critical limit. What happens is the scalar field oscillates back and forth between specific limits, but ever faster and on ever smaller scales. And so the kinetic energy gets driven to infinity, and so does the curvature. And so at the very limiting point, you get, in the precisely critical limit, there's no black hole forming, and you get a naked singularity. And this solution, the scalar solution, has been established rigorously, I guess, depending on your definition of rigor, but it looks pretty rigorous to me, by Rederer and Chubowitz in 2019. So generically, in type 2 collapse then, we can find arbitrarily small black holes. This is sort of by definition. The critical solution is self-similar, possibly discretely so. The precisely critical solution contains a naked singularity, but the formation is clearly not generic. You have to tune infinitely in your parameter in order to get to that critical singularity. But we find these scaling laws for dimensional physical quantities, such as the black hole mass. So again, here we have the black hole mass scaling like P minus P star to the gamma. And once more, we have this notion of universality where there's the same results independent of the specifics of the initial data. And in fact, if you look very closely, if I had more data plotted here, you'd be able to detect a little periodic wiggle. So this isn't exactly linear, this scaling law. There's actually a modification to it, a periodic wiggle, which is represented by this term here, which was shown by Hodden, Perrin, and Gunlack. Okay, so let's talk about the self-similarity in very descriptive terms. So let's use sort of physical variables. So I've got a proper time t measured from the naked singularity backwards. That's the natural time to use. And a physical coordinate such as the areal radius measured outwards from the center of symmetry. And then I can define a similarity variable zeta, which is just r over t. And so the r over t equals constant lines are just these dashed lines shown here. And there's a naked singularity here at 0, 0. So that's the setup in ordinary physical coordinates. Now the natural coordinates to describe the self-similarity in are logarithmically related to those coordinates. So let me do a logarithmic transformation. And I get something like this. So now tau is log of t and rho is log of r. The origin, the naked singularity has been blown up off to the infinite left and upwards from your point of view. And we can see the two types of solutions. If I have a continuously self-similar solution, then any critical function g star of a function of a parameter coordinate, I should say, zeta and tau, is equal to that g star at the same value of zeta at any other value of tau prime. So tau and tau prime are arbitrary. And that's what you see here, where this feature just skates along the similarity lines. The discretely self-similar solution is much the same, except that now there's a non-trivial evolution in scale. But the profile repeats itself every so often in log scale, and that every so often is defined by this parameter delta, which gives us which is the scaling exponent, or what we call the echoing exponent. So in this case, g star of zeta and tau is g star of zeta and tau plus n delta, where n is an integer. And so you can see what's going on here. This is a late time view of the scalar field in logarithmic radial coordinates. And you can see these regular oscillations, which represent the imprint of dynamics, which is occurring on smaller and smaller scales. And the distance between the peaks or the troughs of these waves is equal to delta. So for the massive scalar field, we have for these two exponents, gamma is 0.37 and delta is about 3.44. So you get, under rescaling of about a factor of 30, you recover the same dynamics. So it's quite a rescaling. And it's interesting that that's sort of the largest value of delta that we've encountered so far. Now you can understand a lot of what's going on by doing perturbation theory. And this was done relatively early by Koike and collaborators. And so what we do is we assume some isolated, continuously self-similar solution G star. So this was first done for a perfect fluid, where the critical solution is continuously self-similar. You use G star as a background solution, and then you find eigenmodes f of zeta and eigenvalues lambda I. And then as p goes to p star, you can expand the deviation from the critical solution. So g is a function of zeta and rho, rho being that log of r. And the parameter value p minus g star of zeta and rho is given by this expansion where the ci rho are coefficients. We have the growth factors e to the lambda I rho and the mode functions fi zeta. and CI P star are equal to 0. And the observed critical behavior suggests very strongly that there's a single unstable mode in perturbation theory. So there's one mode for which real of the eigenvalue is greater than 0, and then all the other modes damp as P goes to P star. So that's the basic picture. One mode instability. So if we do that, so we assume that real of lambda 1 is equal to lambda 1, then as P goes to P star, we can do that expansion again. We can, do the Taylor series expansion about P star. The first term drops out. I get a Ci rho e to the lambda I rho Fi of zeta. Again, I do a Taylor series expansion. I get dC1 d rho dP at P star, P minus P star, e to the lambda I rho, lambda 1 rho F1 zeta. And then independent of the scale, black hole formation or peel off to dispersal, which are the two possibilities in the dynamics, and they differ only in the sign of that unstable mode, the projection of that mode in the data. That's signaled by this quantity, P minus P star e to the lambda 1 rho of P is equal to some constant, which will be independent of scale. And if that's the case, then the black hole will form on that scale. So we'll have log of the mass hole of the black hole mass will be log of the radius of the black hole divided by 2, and that will be minus rho of P plus some constant. So taking that and plugging it back in to here, we get the e to the log P minus P star e to the minus lambda 1 log of the mass of the black hole is equal to K1. And that's just the scaling law, that the mass of the black hole goes to some constant times P minus P star to the gamma, with gamma being the reciprocal of that eigenvalue. So gamma is the inverse of the Lyapunov exponent associated with the solution. So finally, we have this phase picture of critical collapse, phase space picture. Yes.
So you said there was these wiggles though, like perturbation theory picture?
No. I mean, it's sort of a case of it can happen, so it does happen, right? So if you look at the scaling for a discretely self-similar solution, you can admit this additional factor on top. And so it occurs, but there's no way of estimating what the magnitude of the oscillation would be. Great. So the phase space picture is as follows. We look at the solution space, and this plane here is a codimension 1 manifold in the space, in the phase space. And in the phase space, there are 2 fixed points. There are only 2 places that the solution can asymptote to. Either you have effectively all the energy gets out to null infinity, or all the energy ends up in a black hole. Actually, there's a mixture of the two in all cases, but let's pretend that that's not the case. Okay, so we have a black hole fixed point, and we have a flat space fixed point. And on the codimension 1 submanifold, we have the critical surface. And so a solution which is exactly in that surface has none of the unstable mode present. So the unstable mode's presence is only felt when you're off the manifold, this codimension 1 manifold. So within the manifold, the evolution will automatically, the evolution naturally gets driven towards the critical point. So if P is exactly P star, then all the stable modes damp, and you get driven to the critical point. So if I have a parameter which is less than critical, then it'll approach the codimension 1 manifold for some amount of time, but eventually it'll peel off and head to the flat space fixed point. Similarly, if I have something which is greater than critical, it'll approach the codimension 1 manifold for some point, but eventually it'll peel off and go to the black hole fixed point. All right. So let me get on to the beyond spherical symmetry then. So I'm going to be looking just at a broad survey of general results that have played out over the past 20 years or so. And I'll culminate with some stuff which is relatively recent on the Einstein-Maxwell theory. So this is axisymmetric scalar collapse of a massless scalar field. So this is Franz Pretorius' PhD thesis, and it's described in a paper that we wrote in 2003. And shown here is the central value of the scalar field for two calculations, the one-dimensional calculation, so the spherically symmetric, and the two-dimensional calculation. So the two-dimensional calculation is the dashed line, and so you start to see some small deviations at the end, but overall the agreement is very good. So these are fully resolved critical solutions. Technically, we had to use adaptive mesh refinement to get the resolution. This is the key problem in getting a good representation of a type 2 solution. You need to get the resolution. As you get closer and closer to the critical point, you need more and more of that. And there's very good agreement then with spherically symmetric code. Now, this is an example of non-spherically symmetric initial data. So this initial data is now slightly prolate. And so you see, as the evolution proceeds, the critical evolution, and it's using a logarithmic radial coordinate along this line of symmetry, which is the z-axis, and this is the rho axis, so we're logarithmic in both of those axes. And so you start to see the critical solution unfolding near the center, but at late times, going over here to the inset, there are actually two centers of attraction where the critical solution is unfolding. And this either indicates some possible second unstable mode, which has an m=2 dependence, or there's something about the initial data itself which tends to concentrate the collapse in two regions. Okay, so ultimately, if you make the data sufficiently prolate, that's the case, that you will pick up two centers of places where the dynamics is being concentrated. But here we weren't sure whether or not we were seeing that particular effect or whether there was a possibility of a second unstable mode. By this point, it had been established in perturbation theory that all the modes, perturbative modes of the spherically symmetric solution should damp. So the expectation was there wouldn't be an additional unstable mode, but we weren't sure whether or not our numerical results were giving a counterexample to what had been shown in perturbation theory again, or whether it was just an indication of some sort of a geometric factor going on. So Baumgart, quite a bit later, did another study where he used spherical polar coordinates. So our calculation used cylindrical coordinates. So he's using spherical polar coordinates. He's using a BSS formulation of the Einstein equations. And he's using a two-parameter family of initial data. But the parameter that we're going to be interested in is this epsilon, which controls the non-sphericity of the solution. So it controls the prolateness of the configuration. And what he found were results which are consistent with ours, but because he was using these polar coordinates, he wasn't able to see the full bifurcation that we saw into two centers of collapse. So we're left with a not quite clear picture of what's going on here, but there, in any case, there's no indication of an additional unstable mode for his results. And here are the scaling exponents. So the spherically symmetric case, he gets very good agreement with previous results. For small departures from sphericity, it's also good agreement. But as he goes up to higher perturbations or higher deformations of the spherically symmetric data, the deviation becomes marked, and it's not clear at all whether he's really picking up a true scaling law in this case, or whether delta is meaningful for those last two cases. Okay. So there's been two studies of this model in 3 dimensions. The first of them was done by Healy and Laguna, published in 2014. And here's some results here. They used as initial data a spherically symmetric profile psi times 1 plus epsilon times a spherical harmonic 2-1 with angular dependence then. So epsilon was a tunable parameter that they could use to control the non-sphericity. And here are the results for various values of this epsilon parameter in a logarithmic coordinate, radial coordinate. And you see that there's evidence of echoing. So they find this evidence for echoing with delta about 3.1 to 3.3. But the calculations don't probe the critical regime very closely. And again, there's no indications of non-spherical unstable mode.
Can I say, and this, even in the previous, the axisymmetric setting, it was a massive scalar field.
Sorry?
In the previous setting with axisymmetry.
Yes, yes,
It's a massive scalar
it's massless.
field. And can I ask, at the profile of the singularity, and when probe the profile, is it similar to the spherical one?
It's exactly the same. Oops. So that's basically what I'm showing here.
So it's becoming spherical, although you didn't start spherical.
This is exactly spherical.
Okay.
So there's very good agreement here between the spherical and the axisymmetric. You can start to see small deviations here. But what's happening here is that there's 2 centers, one here and one here. And so if you had infinite tunability, you would find that you get 2 places where you get this critical solution. So there would be locally exact copies of the original one, but they're surrounded by something non-trivial. Okay. The second example in 3D was by the Cornell Caltech group, Deppy et al., published in 2018. Here they were using the same code that they use for black hole collisions, but specialized for this critical phenomena study. It uses a first order generalized harmonic formulation. They use spectral methods with domain decomposition, using dual frames and a type of AMR called spectral AMR, so that gives them a lot of resolution. They found that they needed to use a specially modified version of their harmonic gauge. And they also found that the constraint damping was crucial. So with constraint damping, you add to the evolution equations multiples of the constraint with controllable parameters. So basically, if you have growth in the constraints, that growth gets beaten down and you get taken back to the constraint hypersurface. So that was found to be crucial, and they found that they also needed significant experimentation with the constraint damping parameters. So here's some results. They got some very nice results. So there's 3 data sets shown here. The blue is spherical data, the red is axisymmetric data, and the green is completely 3D. And here's the plot of basically log of P minus P star and log of the mass of the black hole with some constant, but then they've added a constant in here to shift the curves. So you can see the 3 curves on a single plot. And you see this nice, almost completely linear dependence over a factor of 10 or so in a log of p minus p star. So they get very good agreement with the spherically symmetrical results for the scaling exponent, 0.375 to 0.376. They observe a delta of about 3.2 as compared to the accepted value of 3.44. And again, they find no indications of a non-spherical unstable mode. So here you can see plotted is the logarithm of the minus Ricci scalar, which is a scaling variable, and minus log of 1 minus t over t star, tau over t tau star. So tau is a proper central time, and tau star is a proper central time where the negative singularity is estimated to form. And so these constant factors between these dips are indicative of this factor delta. So you're seeing the solution rescaling on scales ever smaller and ever faster as you approach criticality. They have other methods for computing delta, which give delta of is about 3.46 to 3.56, but overall, they've got very good agreement with spherically symmetric solutions. And again, there's no indications of non-spherical unstable modes. All right, so let's move on to vacuum. So from the point of view of Einstein's equations, this is probably the most sort of interesting case because, of course, there's no matter, and so everything that comes here is purely geometric. And historically, this is the second example of critical collapse to be studied. And it goes back to the same year as my original spherically symmetric massless scalar field results, 1993. And the authors used spherical polar coordinates. They used maximal slicing and quasi-isotropic spatial coordinates. And back in the 90s, we were still using what's known as constrained evolution, where rather than using just a set of evolution equations, we would use constraint equations to solve for certain of the geometric variables on time step to time step. And that's fallen into disfavor, largely because people think that solving constraint equations is difficult, but also because there's no clear way of determining, in a lot of cases, the hyperbolicity of the sets of equations when you put in the constraint equations. Nonetheless, Abrahams and Evans used that sort of system very successfully. And here it was plotted, well, I should finish this. So the mass of the black hole is the apparent horizon mass. The initial data was an ingoing quadrupolar Tucholsky wave. And they used what today seems like a ridiculously modest amount of resolution, just 290 radial by 16 angular grid points, only 16 points in the angular direction. Yet they were able to see this remarkable scaling of the black hole mass, where gamma came out to be very close to that observed for the scalar field. So for a while, it seemed like there might be true universality in the sense that maybe that gamma was universal across models as well as it's being universal across initial data sets. It turned out not to be the case, but for a while it seemed like it might be. Okay, and the line up here is the mass of the configuration in total. So these calculations, 30 years on, still haven't been definitively replicated or refuted. And that's a remarkable fact. So here's an indication of the echoing. So n equals 0, n equals 1, n equals 2, and n equals 3 are profiles of angular of a wave variable on the equatorial slice. So this wave variable eta at these various times, these echoing times when the phase of the evolution is the same. So again, n equals 0, n equals 1, n equals 2 and n equals 3. And then what's shown in these bottom two planes are subsets of these, but plotted using log r plus n delta. So that the ones that occur later in time get shifted relative to the ones which occur earlier in time. And the coincidence of these curves then represents the actual discrete self-similarity. And you see that there's very good coincidence, pretty, for numerical results using the resolution that they were using. It's rather remarkable that these echoes can be resolved so well. And they come up with a delta, which is about 0.6, which is much smaller again than the scalar field, which is about 3.44. So they were lucky in the sense that this delta was small, so they didn't need that much additional resolution to see several echoes. So the resolution you need goes like e to the delta. Yes?
Is this axisymmetry? Is this like a polarized axisymmetry or a general axisymmetry?
It's reflection symmetric about the axis. So if we're in the roads if we were in cylindrical coordinates, we'd have a z goes to minus z symmetry. Same thing in polar coordinates.
But only that, are they d5, d theta terms?
Like it's a D, yeah,
Is
it's
the
orthogonal.
d5 normal to d theta or not?
No,
No, okay, there's no problem. Thanks.
no, it's not. All right. So here's some more recent results on this problem. So in a nice work published in PhysRev Letters a few years ago, Litvinenko and Kirnov again used spherical polar coordinates, a quasi-maximal, so a quasi-elliptic slicing condition. They used the BSSN formalism, so Baumgart, Shapiro, Shibata, Nakamura formalism, which is a way of writing the 3+1 equations in a form which is essentially hyperbolic. They used the Einstein toolkit for their computational infrastructure, so they didn't start from scratch. And they looked at 2x2 initial data families, a Brill wave, and then one which had a conformally flat 3-metric with a perturbation and one extrinsic curvature component. So they call this time asymmetric or TA data. In both cases, the sign of the amplitude leads to a distinct family. And so that's where the 4 families come up. 2 for each of the Brill wave and the conformally flat approximation, or the conformally flat data, I should say. To analyze, they looked at invariance. So they looked at the Kreutzmann scalar. They also looked at zeta, which is a circumferential radius invariant. So the circumferential radius is rho. And so this combination 1 minus rho, the gradient of rho squared divided by rho squared, is a geometric invariant that you can use to characterize what's going on geometrically. And they tuned to about 1 part in 10 to the 7th. So not full tuning, not a part in 10 to the 16th, but about a part in 10 to the 7th. And this is a very busy plot, but what you should really take away from this, which is plotted here, is the maximum of a scaling factor times the 1/4 power of the Kreutzmann scalar versus log of p minus p star. And what you should see is that basically we've got scaling. So there you can drop a fairly linear line through any of these particular curves, the TA greater than 0, TA less than 0, the Brill greater than 0, the Brill less than 0. And you come up with these estimates for the exponents, the mass scaling exponent. So there's something going on for the minus for the Brill case. The Brill isn't behaving in the way that the Abrahams and Evans calculations did. Right. So here's a plot from which you can sort of see the echoing. So on the right-hand side, so basically there's a radial coordinate being plotted here and a temporal coordinate being plotted here. So the z coordinate on the x-axis and the temporal coordinate on the y-axis. And so on the right-hand side is an evolution of the massless scalar field. And so you can see these contour plots look like rescaled versions of themselves. So that's the echoing down to smaller and smaller scales. And you can also see that it's happening in coordinate time relatively quickly, going from 2.06 to 2.12 in this case. And that's characteristic of the scalar collapse. It happens quickly and the signal is very strong. The signal for the gravitational case is much weaker and it unfolds over a much longer time. So here we're going from 10 to 25, but you can see indications of the echoing. So this looks like a rescaled version. This looks like a rescaled version of this. Similarly here, we've got this evolution in here is rescaled to give us this in here. Okay, so that's the indication of the echoing. And there's more echoing evidence that we can produce by looking at this quantity zeta, this circumferential invariant, chosen so that rescaled by a factor of lambda, with the time tau naught also being rescaled by a factor of lambda, where this lambda is chosen so the minimum value of zeta naught for any data set is equal to 2. And if you do that, then the curves all collapse down on top of one another. And you get this curve for the 4 data sets. That's for the 4 different calculations. And you get the top for the different echoes. So this is strong evidence that they're seeing echoing, although it remains more difficult for them to actually extract the echoing period than it would look like from these calculations, from this plot. So that's a technical point that I won't get into. All right. So the most recent work came from a collaboration between 3 different groups, one in Prague, one in Germany, and another one basically based around Thomas Baumgart's in Bowdoin College in the States. So the first effort used BSSN and spherical coordinates. We just talked about that. The second used a generalized harmonic, a multipath pseudospectral technique. And the third used BSSN with spherical coordinates and a particular type of slicing which avoids shocks, which was very useful for them. They focused on axisymmetric Brill waves with this particular initial data. So this is the 3 metric. And the factor Q, which is the Brill wave, has this Gaussian form. This shows how much coincidence there is between the 3 models. So the X's are the BAMPs, the circles are the Prague, and the squares are the SPHGR. And you can see that in this region here, where all 3 of the codes, and in this region here, where all 3 of the codes are active, there's extremely good agreement between the 3 codes in terms of this quantity, which is P minus P star, and the maximum value of the Kretschmann, which is encountered during the evolution. So we can see some signs of the echoing. So here we have on the left-hand side the calculations from the BAMPS code. On the right, we get the calculations from the Prague code. This is a very busy looking slide. So this is, again, Kretschmann to the 1/4 that's being plotted. But you can untangle some of this by looking at a rescaled version of this, which is drawn along similarity lines. So now the coordinates lambda and tau are determined by similarity or pseudo-similarity lines. And what you see here is extremely good agreement between the 2 codes. And you can see the evidence of echoing as we go from here here to here to here. So in this case, we've got the opposite sign for that family, and there's no apparent echo. So if you do the same sort of unwinding of the solution in terms of similarity coordinates, you don't find any evidence of echoing. So there's good agreement amongst all three codes. There's evidence for the discretely self-similar solution with the same echoing period previously seen by Abrahams and Evans. But for other initial data, there's no evidence for discretely self-similar solutions. So the conjecture or the claim that there's no universality for axisymmetric collapse of gravitational waves. But the caveat here is that the critical solutions are not that finely tuned. And so we don't know what's really going to go on in the limit that the tuning goes to infinity.
It seems to be discretely self-similar and universality are two different things.
Right.
You said there's no evidence of discretely self-similar, but in addition, there's no evidence of universality. So I see a different profile. Right?
Well, the discretely self-similar comes with a solution.
Sure.
So if there's a different solution, there's going to be a different discretely self-similar behavior.
Okay, but there are two different solutions. Both of them are discretely self-similar.
Maybe.
But just, okay.
Maybe. The evidence here is that it's not.
Not even that.
Yeah, that's right. There's no discretely self-similar behavior in one of the families of the solution.
I see.
All right, so let's go on to the Einstein-Maxwell collapse. So here, Mendoza and Baumgart studied the critical collapse for two families of initial data, dipolar and quadrupolar. Again, as with the case for the gravitational collapse, you can't have an exactly spherically symmetric solution. So they found evidence for critical scaling with distinct exponents for two families, for dipolar and quadrupolar, but there's different exponents, gamma, in the two cases, and different deltas in the two cases. So it looked like there were distinct, discretely self-similar solutions for those two cases, and they conjectured there's no universality in the model. I'll skip this. So Gray Reed, for his PhD thesis, took a look at axisymmetric Einstein-Maxwell collapse as well, used a generalized BSSN formalism and cylindrical coordinates, used the coordinate conditions that the derivative of A was equal to -2, derivative of alpha was equal to -2 alpha times K, so it's so-called driver condition and zero shift. Again, use of Berger and Oliger adaptive mesh refinement was crucial, and he didn't have to add any explicit constraint damping terms. So the scheme remained manifestly scale free. So there wasn't any additional scale introduced into the system that the constraint damping terms would normally. And we studied four different matter initial families, data families, an electric dipole, a magnetic dipole, a magnetic quadrupole, and an electric quadrupole from Mendoza and Baumgart. And for the dipolar data, you find the collapse unfolds at the origin. But for the quadrupolar data, what happens is that at early times, the critical behavior looks like it's unfolding at the origin, but then it splits off, and again, there's two centers, like there were in that prolate collapse of the massless scalar field. Okay. So this is a calibration of the code for a massless scalar field, which shows that the code works very well. Scaling of the energy density for the massless scalar field. So this isn't the Maxwell field yet. Gives the scaling exponents as we expect. Same thing for the scalar curvature. And then this is the weak field, the near critical evolution of the magnetic dipole data. So here's the lapse bouncing around, and you don't see too much. You'd have to take a Fourier transform to really see what's going on. And the logarithm of the square of the field strength tensor as a function of minus log of tau star minus tau, and you see the echoing behavior. And the same thing for the electric dipole data. Again, see the echoing behavior. And what happens for the magnetic quadrupole data is that at early times on the left, there's some characteristic oscillation frequency, so some characteristic delta. Then there's a transition period. And then at late times, the oscillations occur with a larger delta. So this is the migration of the center of the place where the critical behavior is occurring from the center to the off-center location. And so if you do the fits, so to the left is more critical, so to the right is less critical. So the fit along here gives an exponent of 0.073, whereas the fit here is the near critical point where the critical behavior has gone to the off-centered position, then you get gamma of about 0.145. And for the other two cases, the electric and the monopole, the electric and magnetic dipoles, we get gamma of 0.147 and 0.152 respectively. This is a comparison with Mendoza and Baumgart. So it's remarkable how well these codes agree. You can't see the deviation until the late time, which is blown up in here. Here's the scaling of the EM invariant. So again, we get the roughly constant scaling exponents, but only if we fit to the late time behavior and don't include the early time behavior. So a final table, here's the values of gamma and delta. So 0.147, 0.152, 0.145, 0.152. There's good indication of universality here as long as we exclude the early time behavior in the quadrupole data, which is this line here. And this line here. So the results are consistent with universality for this set of families. But you had to tune quite close to criticality in order to see that. So I'll just finish up. The key question then, or a key question, is there universality in the non-spherical critical collapse case? So the indications from our work are that you really may need a lot of tuning in order to see what's going on. And so some of the results in vacuum just may not have been tuned closely enough. So we'd like to be able to tune beyond current limits, which is real star 8 arithmetic apart in 10 to the 16, but the calculations are expensive as is. So the question is there some way that we can get rid of this need to run a whole bunch of simulations where we do some sort of bisection search in order to find the critical point? Could we do this, find these solutions directly through iteration rather than indirectly by a series of bisections? And so that's something I've been thinking about. But the fundamental question is, what reason do we have to expect universality? Why should these solutions be universality or sort of unique? Why couldn't we have more than one critical solution in particular cases? And there doesn't seem to be a good reason why we shouldn't be able to. So that it just may turn out that the universality is not achieved. And then finally, it would be really nice to be able to describe these solutions in a more geometric fashion. Because if they have these aspects like this discrete self-similarity, which is really easy to describe in spherical symmetry, it would be nice to be able to describe that in a more invariant way in a more asymmetric situation. And that's it.